Yes, we are discussing the concept of hybridization in the chapter chemical bonding. Well, first of all, before we get into the applications of hybridization concept, briefing about what is the reason why we are taking up what hybridization concept, you must be knowing. Once you know the basis of the necessity of having hybridization concept, then I think you can go in for the applications part, right? First of all, understand, before this theory, we used to have valence bond theory proposed by Linus Pauling. He was going great, but he is limited to only explain some of the shapes of diatomic molecules like oxygen, nitrogen, HCl, HF, and few diatomic molecules which were explained beautifully. There was a beautiful explanation for that. How a single bond is formed, how a double bond is formed, how a triple bond is formed, how he basically rules out during covalent bonding. It is not the atoms that are overlapping, but rather the atomic orbitals inside the atoms that are actually overlapping, and holding these two atoms together was the concept which was introduced by Linus Pauling. That was fine, great. In fact, his introduction of the concept of overlapping is one of the biggest merits even we carry forward, and we will be carrying forward in chemistry, you must understand. So we will be carrying forward his concept of what overlapping. But that's on one side where he beautifully explained the shapes of diatomic molecules, right? Shapes of diatomic molecules, and he introduced the concept of overlapping. All that is fine. But whenever you speak of a bond angle with Linus Pauling and pose a question on valence bond theory, he was not able to explain, right? So for bond angles, that means I'm referring to polyatomic molecule structures and the bond angles. Polyatomic molecules and the structures of bond angles, if you ask Linus Pauling, he not only fails but miserably fails, and sometimes the explanation given seem to be seriously flawed and ridiculous rather, right? And one of the biggest drawbacks of valence bond theory is he could not explain the shapes and the structures, bond angles of polyatomic molecules. For example, polyatomic means more than two atoms, right? He cannot explain ammonia, he cannot explain H2S, he cannot explain water molecule, he cannot explain beryllium chloride, beryllium fluoride, and all this because they have more than two atoms, right? And if you apply also, it seemed to be absolutely seriously flawed is his theory. You must understand that, right? That's one point. The second thing, what is very silly is, at the nick of the moment when the bond is about to establish, right, two orbitals from two different atoms are coming and approaching for overlapping, then the direction of that is absolutely not fixed. For example, I'm referring to a projection of the p orbital vector onto S is absolutely not fixed. That means that you will not be able to actually, if this is the s orbital of one atom and if this is the p orbital of another atom, this direction, this projection onto S for the overlap is absolutely not fixed. This is absolutely not fixed. So the p projection onto S is absolutely not fixed, whether the p orbital has to come linearly, acutely, obtusely, or with a certain bond angle is absolutely not fixed. That too at the time of bonding, at the 11th hour, well, he is trying to discuss all these things is absolutely nonsense. That actually sow the seed for go out and check out for some other theory, and then convincingly explain the bond angles of the polyatomic molecules and remove all these flaws where the p orbital onto S we cannot explain, and the bond angle is not fixed, and the structures are not cannot be detailed. If this is the case, then that forms the necessity for what the concept of hybridization. And what is the biggest feature of the hybridization concept is this hybridization happens, it's a hypothetical theory. It's absolutely hypothetical theory. One more thing I wanted to tell, that we are not, this hybridization or valence bond theory or any other theory which I will propose from here on, they are not methods of preparations for molecules. Molecules are already there. These are not methods of preparation. The molecules are already there, they are formed in the laboratory, they are already existing, their bond angles are also determined. Everything has been determined. The only thing is we are trying to propose a theory which will explain convincingly that particular bond angle, that particular shape, that particular structure, and all these things. So we require definitely a theory which will convincingly explain the bond angles of polyatomic molecules and removes the serious loss of p projections onto s. Right? And one of the biggest features of hybridization we were discussing is all this happens before bonding. All this happens before bonding, and before bonding within the atom. And they intermix, what intermixes? The orbitals, the atomic orbitals inside the atom. The atomic orbitals inside the atom before bonding in excited state, about to participate in bonding, they get into excited state, intermix, and then generate totally different orbitals which are called hybrid orbitals. And one of the biggest feature of hybrid orbitals is they have better directional properties. When I say better directional properties, these flaws are actually removed. That means that in simple language we can say before bonding itself, the atomic orbitals are sitting in certain positions and the positions are fixed, the bond angle is fixed, everything is fixed, I am ready, and now the partner comes and overlaps and the bond is established. So the biggest merit of proposing this hypothetical theory is all this happens before bonding, in excited state, they intermix, right, and then generate a new set of orbitals which are called hybrid orbitals, which have the bond angles fixed before bonding, structures are fixed before bonding, and everything is fixed before bonding itself. That is one of the striking features of what hybridization. You must understand that, right? And I was telling you, you have several molecules outside. You have many molecules outside, and the student faces a difficulty in understanding which type of hybridization is taking place in which central atom. Right, this has been a big issue for him, right? So for that, in fact, I was proposing a formula to you, if you can recollect that. For judging hybridization, let me check quickly. For judging hybridization, you use the formula H is equal to half into V plus M minus C plus A. This is the formula what we will use. Now, what is H here? I was telling you, it is the number of hybrid orbitals. It is absolutely must to know the number of hybrid orbitals generated. Then only we are in a position to determine the hybridization. You must understand. How do you determine? Is simply if H is actually 2, it is SP. If it is 3, it is SP2. If it is 4, it is SP3. If it is 5, it is SP3D. If it is 6, it is SP3D2. And 7, even SP3D3, you must understand. So the H value, if you are arriving at the H value, then you are in a position to determine the hybridization. And to arrive at the H value, you have a formula which is half into V plus M minus C plus A. Now what is V is the number of valence electrons of the central atom. If you don't know the number of valence electrons and if you feel tedious writing the electronic configuration, then remember that it's a group number. Valence electrons, not valency. The number of valence electrons which you have in the outermost shell, that itself is group number. So if you are dealing with carbon, it belongs to fourth group. If you are dealing with nitrogen, it belongs to what? Fifth group. If you're dealing with oxygen sulfur, it belongs to sixth group. If it is halogens, you belong towards seventh group. You must understand if it is boron, your aluminium, you are dealing with what? The third group. So you need not write the number of valence electrons, at least know the group number. That is what? The valency. M is the number of monovalent atoms attached to the central atom. Monovalent atoms in chemistry are only two, that is hydrogens and halogens. So count the number of hydrogens and halogens and put it. C is the cationic charge. That means in case of cations, if you are determining the hybridization, you need to put the charge, not the sign. And A is anionic charge, you need to put the charge and not the sign. For example, I'll give you all the three ones. Observe carefully here. Suppose if you wanted to take BCl3 and you wanted to know the hybridization of boron. So then H is equal to half into, right, boron is third group, number of monovalent atoms. Well, I say monovalent atoms are nothing but number of hydrogens and number of halogens. Number of hydrogens and number of halogens attached to the central atom. Now you can see the number of halogens are 3 attached to the central atom, that is 3. So I just put it to be 3. It is not a cation, so it is 0, no charge. It's not an anion, so no charge. So 3 plus 3 is 6 by 2, which is 3. So H value is 3, then it is sp2. H value is 3, it is basically sp2. That's what you need to remember this. For students who are writing the exam, if you wanted to know which type of hybridization is taking place in a certain species, then use this formula. And the second thing is, if I can take you an anion, suppose if it is a sulfate ion, then if you can go for sulfate ion, then H is equal to half into sulfur belongs to 6th group. Sulfur belongs to 6th group. If you don't know, write the configuration of sulfur, you will find it out that in the outermost shell you have actually what, 6 electrons, right? So it belongs to 6th group, and if you see the number of monovalent atoms attached to the sulfur, it is hydrogen and halogens. You don't find hydrogen and halogens in the sulfate ion, it is oxygen, and oxygen is bivalent, and we are speaking of monovalent atoms. So they are 0. You don't have monovalent atoms, so it is 0. Is it a cation? No, it's not a cation. It's not a cation. So charge is 0. Is it an anion? Yes, of course it is an anion. So charge is 2. Remember, you need to put the charge, not the sign. It is the charge which you need to put it. You don't, everything is adjusted in the formula. You don't put it to be -2. Whatever is the charge on the anion or cation, you need to put it. So this is +2. So this is 8 by 2 is basically 4. And if H is equal to 4, it is sp3. You can see here, if it is 4, it is sp3. The sulfur is basically undergoing what? An sp3 hybridization, you must understand. You can take a cation, you can see here. If I take a cation and explain to you, then H is equal to half into carbon belongs to 4th group. It belongs to 4th group, right? So it is 4 plus number of monovalent atoms attached to the central atom, that is 3 hydrogens are there. Of course, hydrogen is monovalent. Just put it to be 3. 3. Is it a cation? Yes, it is a cation. So the charge is +1. So it is -1. It's minus, and the C is the cationic charge, that is 1. Plus it cannot be an anion now. 7 minus 6 is 3. This is 6 by 2, which is 3. If it is 3, it is sp2. If it is 3, it is sp2. That is how we judge the hybridization in a given species, and I gave you an example of a neutral molecule and an anion and a cation. So you must be aware of what the hybridization is in a given species, because you will be given so many species and the hybridization must be fixed for you in advance, right? So that is how we judge it. Now the question, coming to the main part, that is the applications of hybridization, as I said, he will be asking you the number of pi pp bonds and pi dp bonds in the exam. He will ask you the number of pi pp bonds and pi dp bonds in the exam, right? That is the main question. Now, by asking this, he's actually wanted to test you the complete details of hybridization. You have it in your mind or not. You have gone through the preparation of the hybridization or not. But otherwise, why will he ask the pi pp bonds and pi dp bonds? Right? What are pi dp bonds? What are pi pp bonds? Let us understand. Pi pp bond. First of all, pi. What is pi? Pi is the result of a sidewise overlap. Pi results in the sidewise overlap, and head-on overlapping results in a sigma bond. You must understand. And pi bonds are always formed by pure orbitals, pure orbitals. Now, what are pure orbitals? That which don't participate in hybridization. You must understand. So, pi pp and pi dp. Now, what is pi pp? pp is the result of p and p overlapping sidewise. Pi dp is the p and d overlapping sidewise. You must understand, right? So the pure orbitals pp, you get pi pp. The pure orbitals overlapping p d, you get what? Pi dp. You must understand. P and d is pi dp. pp is what? Pi pp. And he will ask you count the number of pi pp bonds and pi dp bonds in the exam. That is a critical question. Well, I would like to give some examples and go into the details of it, and let's write the draft for it, right? And this is a question which you can bank on. So let us go quickly and find out some of the pi pp and pi dp bonds here. Observe carefully here. Watch carefully here. The questions which he will be asking is, calculate number of pi pp bonds and pi dp bonds in sulfur dioxide, sulfur trioxide, sulfate ion and sulfite ion. You must understand. SO4 minus 2 and SO3 minus 2. This questions I have seen asked very frequently, calculating pi pp and pi dp bonds. By asking this pi dp and pi pp bonds, is actually wanted to test you whether you have gone through the entire details of what hybridization and are you acquainted with it. That is the intent of asking such questions, right? Now, first of all, let us take the case of sulfur dioxide. Remember one point here. Remember one point, the sulfur dioxide looks like this. That is the sulfur dioxide, you must understand. That is the sulfur dioxide, you must understand, right? And if that is the case, then we need to explain how this bond is formed, how that bond is formed, how this bond is formed, how is that bond formed. First of all, in a double bond, you have a sigma and what? 1 pi. In a double bond, you have 1 sigma and 1 pi. Remember, we are not preparing compounds. Compounds are already existing there, right? We just need to explain a theory, apply a theory to convincingly explain why sulfur dioxide is basically taking this shape. This is what we need to explain. And in the exam, he is asking us to count pi pp and pi dp bonds, right? So let us go straight away and check out, first of all, what is the hybridization in sulfur dioxide, right? Then H is equal to half into, sulfur belongs to basically 6th group. It belongs to 6th group. So H is equal to half into V plus monovalent atoms. The number of monovalent atoms is 0 here because you don't find hydrogen and halogens attached to sulfur. So H is equal to half into V plus M minus C plus A. M here is 0 because you don't have hydrogens and halogens. So it's basically 0. It is not a cation. It is not an anion. So it is 6 by 2, which is 3, and it is sp2 hybridization. It is basically sp2 hybridization. So remember, we are sticking in this discussion only to count the number of pi pp bonds and pi dp bonds, which he will be asking in the exam. That is our point of discussion. Nothing beyond that, right? So let us start the draft and check it out how we can do it. For example, since the hybridization is fixed now, then what I will do is this. In sulfur dioxide, here is the draft. Here is the draft, which is standard for writing all what the hybridization details of every compound. The draft should have all these important points. So I write it. In sulfur dioxide, the central atom. Now what is central atom? Central atom is the one which the hybridization is taking place. Well, I'm getting ready for the partner to be called. That that readiness happens in one atom, that is nothing but what? The central atom, and the central atom here is sulfur. Right? So in sulfur dioxide, the central atom, sulfur, undergoes sp2 hybridization. Now, how did I conclude that it is sp2 hybridization? You can check it out with the formula in advance itself. You can see here I got H value 3, which is sp2 hybridization. So I'm very confidently writing in the draft. So in sulfur dioxide, the central atom undergoes sp2 hybridization. That's what it is. Now let us go in for the GSC of carbon, the GSC of sulfur. GSC, I mean ground state configuration. The ground state configuration of sulfur. And I wanted to write the outermost configuration. The total configuration is sulfur is 16. So you can write it 1s2, 2s2, 2p6, 3s2. Right? I wanted to write the third shell. So I would like to write rather the outer GSC. The outer GSC of sulfur, outer GSC. This will have 3s2, 3px2, 3py1, 3pz1, and the third D is completely vacant. 1, 2, 3, 4, and it is 3d0. Rather, the entire d orbital is what? Vacant. The entire d orbital is vacant because it is the third shell, and the first shell will have only 1s, second shell will have 2s, 2p, third shell will be having 3s, 3p, 3d, right? It is vacant. Now, this is the ground state. This is the ground state. I'm sleeping in the ground state. I'm not excited. I'm not excited at all. When you're not excited, don't have any intent of participating in bonding, you absolutely have no intent of participating in bonding. You're sleeping in the ground state. This is how the sleep looks like. You can see here. So total 16. So 10 I didn't write it because the outermost shell I'm writing it. 10, 12, 14, 15, 16. And the entire D is vacant. And now I'm sleeping. This is the ground state. Now when I'm sleeping, someone prompted me. Who is that? This is the oxygen atoms. 2 oxygen atoms. 2 oxygen atoms. They prompted me and they told me that yes, we wanted to participate in bonding with you, and we approach you. So you can expect the 2 oxygens coming towards me. And the intent is to participate in bonding. Both the oxygens are coming towards me, approaching me. When they approach, they vomit energy. When they vomit energy, that energy is eaten away by sulfur. And when someone is eating the energy, you rise to an excited state. Because we were told in atomic structure and in the quantum mechanics that the difference between a ground state atom and an excited state atom is basically nothing but a quantum of energy. It's nothing but a quantum of energy. Now what's a quantum? H nu, 2 H nu, 3 H nu, 4 H nu, n H nu. You can't have half H nu, 3 by 2 H nu. It's quantized. It's a multiple of H nu. You must understand. So when I was sleeping like this in the ground state, oxygens are approaching me. And they are approaching me for the intent of participating in bonding. They are vomiting energy. That energy is eaten away by me, and then I rise to the excited state. I must be rising because hybridization occurs only in excited state. And the excitation cannot be exponential. You should be actually slowly getting excited. You just can't excite to the highest level. Right? So the oxygens are approaching and the energy is vomited. So I go to the excited state and I go first to the first excited state. Right? What is the first excited state? Look here. The first excited state. First excited state configuration, because I have eaten the energy. And the difference between these two is H nu, N H nu. It has eaten away certain energy given by what? Oxygen. So you rise to an excited state. In the excited state, what is happening is, look into this. This one of the X electrons are actually kicked to D. Right? If I can write it, this is how it is. 3s2, 3px1 now, 3py1 now, 3pz1 now, and you have the entire D vacant, right, and kick one electron over here. So you look into this excited state configuration, one of the p electrons are kicked to D because the entire D is what? Vacant. This only happens in excited state, not in the ground state. So I'm actually preparing myself for the bonding. Now why do you want it to prepare in this fashion, you might be asking. Remember, if you look into the oxygen configuration, it has 2 unpaired electrons. If you wanted to write it, this is how the oxygen will be looking like. If you look into the oxygen configuration, this is how it looks like. Is 8. So 1s2, 2s2, 2px2, 2py1, 2pz1. You can see 2 unpaired in oxygen. So one of the oxygen, when it approaches sulfur, it is actually coming with 2 unpaired electrons. 2 unpaired electrons. So like that, there are 2 oxygens coming and approaching sulfur. So each oxygen is coming with 2 unpaired. So total 4 unpaired electrons are coming with 2 oxygens. And you know that only unpaired electrons participate in bonding, not the paired fellows again participating in bonding. So when both the oxygens are approaching sulfur, they are getting actually 4 unpaired electrons. So I myself must be getting ready with 4 unpaired such that I can have a pairing for unpaired versus unpaired. So that I can get it only when I get excited and stop at first excited state. How many unpaired you required? You required 4 unpaired because each oxygen is approaching you and coming with 2 unpaired. So total is 4 unpaired electrons you must be having. So I got excited and stopped here because in the first excited state you see here, you have 1, 2, 3 and 4 unpaired electrons. That is the entire outermost shell. So I got excited and now in my pocket I have 4 unpaired electrons ready to be paired with both the oxygens. But I am not in a hurry. Before I participating in bonding, well, I'll be making sure that I sit in certain positions. Well, I sit in certain positions, certain bond angles. The structure is fixed. the bond angles are fixed, everything is fixed, then only I will call the partner. That is one of the striking features of hybridization. Before participating in bonding, everything must be fixed, right? So now I am in the excited state. Before calling the partner, let me sit properly. Sitting properly is nothing but hybridization. And what hybridization is taking place here? We already found out it is sp2, and you started off the draft by writing that it undergoes sp2. So why don't we lock it? 1s and 2p's. 1s and 2p's. Mind you, 1s and 2p's. This is the lock. This is basically the hybrid lock. Now this is leftover, so that is pure. And this is also what? Pure. This is pure P, this is pure D. Those two are left out of the hybridization. So hybridization is only 1s and 2p's. 1s and 2p's. The remaining two are left out of the hybridization. Anything which is left out of the hybridization is considered to be pure orbitals, and pure orbitals always form pi bonds. They never form what? Sigma bonds, right? So let us write it now. So it is 1s and 2p's. Let us write it. 1s and 2p's have participated. 1s and 2p's, 1s and 2p's, giving you 3 sp2 hybrid orbitals, giving you 3 sp2 hybrid orbitals. 3 sp2 hybrid orbitals. Why don't I draw it? 3 sp2 hybrid orbitals. Look into this. 3 sp2s. 1, 2 and 3. This is sp2. This is sp2. This is sp2. 3 sp2 hybrid orbitals I am drawing. And in the log, count the total number of electrons, 2, 3 and 4. So in the lock you have 4 electrons in the lock. Now we need to distribute this in 3, and we have to follow Hunt rule. So start first 1, 2, 3 and 4. And 4. So the lock contains 4 electrons, and with the 4 electrons must be distributed in the 3 compartments. So if I can distribute, it is 1, 2, 3 and 4. This is already paired. So this is what is called a lone pair. This is called the lone pair. Since it is paired electron, it will not participate in bonding. Now the 2 unpaired electrons are there in 2 sp2s, and don't forget this pure P. Bring it down. This is pure P left over. This is pure P, and it has 1 electron here. And this is also pure D. Pure D, right? So you understand, this is pure D and it has 1 electron, right? Now I am ready. Ready with what? 4 unpaired electrons. You can see 1, 2, 3, 4, out of which 2 are hybrids, 1 is pure, 1 is pure. Now I am ready for the bonding. What we will do, we will call first 1 oxygen, and the oxygen is coming with 2 unpaired. 2 unpaired. 1, it pairs with the sp2. It forms a sigma bond. The other unpaired will be pairing with what? P. That gives you a pi bond. So let us reconstruct it. Let us reconstruct this. Watch carefully. I am reconstructing this. I reconstruct the structure. Watch. I reconstruct the structure. Watch carefully here. Right? Let us reconstruct it. So I have 4 unpaired, 1 oxygen is coming now. 1 oxygen is coming. With how many unpaired it is coming? 2. One of them will pair with this. One of the oxygens, unpaired, has paired with this. Let us start off. This is the sulfur, right? And now here is a sigma bond. Because the oxygen has brought 1 unpaired electron and it is pairing with sp2. And this is sigma bond. So when this is sigma bond, it is basically a result of what? How is this bond formed? sp2p sigma. So sp2 of what? The sulfur, and the p of what? Oxygen. Right? So sp2 and p. because oxygen is coming with two unpaired electrons. One of the unpaired is paired with what? The sp2 of sulfur, and the other one, and of course what? P of what? Oxygen. So what is this overlap basically? Why is this sigma bond formed? Is basically it is a result of sp2p, and it is a head-on overlap, that is sigma. That is what it is. So basically, how is this sulfur-oxygen bond formed? This is formed because of the overlapping of sp2 of sulfur and p of what? Oxygen, and this is a head-on overlap, and it is sigma. Because each oxygen is getting two unpaired. One I fixed it. That is a sigma bond. Because it has now paired with what? Hybrid. You are left with one more unpaired. That will now pair with this pure p. So now you have the pi bond, and this is a result of pure P and pure P. Pure P of what? Sulfur, and pure P of what? Oxygen. So it is basically nothing but a PP sidewise overlap, which is resulting in a pi bond. So this is basically a pi bond, which is a result of, this is a pi bond, which is a result of PP overlap. PP overlap, and that is a pi PP bond. You must understand. Why is it called a pi PP bond? Because it is the pure P of sulfur which is overlapping with the pure P of what? Another oxygen. You must understand. Another oxygen. So that is one oxygen finished. The other oxygen is coming. The other oxygen also coming with what? Two unpaired. So then again it will come and hit this sp2 with the oxygen, and then again a sigma bond is formed. This is sigma, and this is the result of sp2p, right? That is a sigma bond. I have another unpaired electron. Now I need to pair it with this. Remember. And here is another pi bond, and this pi bond is a result of dp overlap. D, because this is pure D of sulfur, and the P of what? Oxygen, which is resulting in what? A pi dp bond. You must understand. So if you count it, look into the question. What are we doing? Calculating number of pi pp and pi dp bonds. Calculating pi pp and pi dp bonds in these species. This is what we are doing. So if you wanted to calculate now, you can check it. Now, pi pp bonds are how many? It is 1. Pi dp bonds are how many? It is 1. Total number of sigma bonds are how many? 2. This will be the questions in exam. These are the questions in exam which one must be acquainted. You must understand that, right? Calculating number of pi pp and pi dp bonds, if he is asking, he just wanted to test your in-depth knowledge and your acquaintance towards the concept of hybridization. You must understand. Now people might ask me one thing. What happened to this? This is a paired electron. What happened to this? Where is it? You can show it here, and this is how it is. This is one sp2 which has a lone pair, which is occupied by lone pair. So if you wanted to count the number of sp2 hybridol involved in this hybridization, total sp2s are 3. If you can show here, one sp2 is having a lone pair, the other sp2 is involved in sigma bond, the other sp2 is involved in sigma bond, and these two pi bonds are the result of the overlap of pure P of oxygen and pure D of oxygen, or pure P of oxygen and pure P of what? Sulfur. So then you have pi bonds, because pi bonds are always out of the hybrid lock, you must understand, and hybridization orbitals always form sigma bonds. You must understand that, right? So let us take another example and check out how many pi pp bonds and pi dp bonds will be present in case of what? Let's take the case of an anion. Let's take the case of an anion and check it out. How many pi pp, how many pi dp bonds are there? And this is tested because to check the in-depth knowledge of what you have towards the concept of hybridization. Let us take the case of the sulfate ion. Let us see this. Calculating number of pi pp and pi dp bonds is of course a question in the exam, you must understand. Let us take the case of sulfate ion. the case of sulfate ion. Now, what are we doing here? We are calculating number of pi pp, pi dp bonds in sulfate ion. Pi pp and pi dp ions in the sulfate ion. This is what we are supposed to do. First of all, as I said, we are not preparing sulfate ion. Sulfate ion already exists, right? It exists. And we are supposed to only tell how the structures are formed, and we have to back with a theory. So there should be a theory backing for the ions which are available. And the sulfate ion looks like this. We wanted to know where the charge is, the -2 charges. So I'm drawing the sulfate ion for you. First you get acquainted with the Lewis structure, then we will cater and push a theory to explain that. And sulfate ion looks like this. First of all, in sulfate ion, you have 1 sulfur and you have 4 oxygens. The sulfate ion is basically having this. 1 sulfur and 4 oxygens. Now we wanted to know where the charge is. The charge is not on the sulfur, it is basically on the oxygen. So if you wanted to say this, then it is 2 oxygens are fine, you have minus on 2 of the oxygens. You must understand. You have 2 oxygens, right? You have a charge on the 2 oxygens, not the sulfur. So the sulfate ion will be having 1 sulfur, 4 oxygens, 2 oxygens are having minus sign. Now, how the sulfate ion looks like, the structure is somewhat like this. This is O minus. This is the double bond. This is the sulfate ion, you must understand. That is the sulfate ion. Remember, how I am drawing Lewis structures is basically I know which group the sulfur belongs to. The sulfur belongs to the 6th group. So if an element is belonging to the 6th group, maximum number of bonds it can form is 6. It can form maximum 6 bonds. It can be 3 double bonds or 2 double bonds or 2 single bonds or whatever. There are permutations and combinations for 6. It's up to you. But the total number of bonds which are formed are only 6. Right? And look here. Now look here. Total number of bonds. 1, 2, 3, 4, 5, 6. So we are sticking to the fundamentals of chemistry. Now what are the fundamentals of chemistry? That any element belonging to the 5th group, it will form 5 bonds. 4th group, it will form 4 bonds. 6th group, 6 bonds. Like that, it depends on the group number. You must understand. Since sulfur belongs to 16th group or the 6th group, what we say, the total number of bonds are 6, and I am right in writing this. In this notice, there are 2 pi bonds and the other 2 are what? Oxygen atoms bearing minus charge. So this is basically giving you the sulfate ion. So understand that the charge which is present, negative charge, is basically on oxygen and not sulfur. An oxygen and not sulfur. Must understand. So what we will do first, before we start the draft, let us actually go and check out the hybridization in advance. Let us do that. Watch carefully here. Look into the hybridization. What is hybridization? How do you find it? H is equal to half into V plus M minus C plus A. Now this will be equal to half into valency of sulfur, which is 6, group number, which is 6, and M is the number of monovalent atoms that are attached to the sulfur. I don't find any monovalent atoms because monovalent atoms in chemistry are hydrogens and halogens. Well, I don't find them, so it is 0 because you find oxygens here. So it is 0. Is it a cation? No, it has a negative charge. It's not a cation. But yes, of course, it is an anion. And it has a double negative charge. So it is a -2 charge on sulfate. But as I said, when you wanted to put the A, which is anionic charge, only put the charge, not the sign. So the charge on the anion is basically 2. So it is plus 2. That is 8 by 2, which is 4, which is sp3. So in advance, I have predicted the hybridization of sulfur in sulfate ion to be what? sp3 hybridization, you must understand. So let us start the draft. Let us start the draft very quickly. And remember, what are we doing here? We are calculating the number of pi pp and pi dp bonds in sulfate ion, which he will ask in the exam. You must understand. Right? Let us start the draft. In sulfate ions, central atom sulfur undergoes sp3 hybridization. When it is sp3 hybridization, everything is fixed. The bond angle is 109 degrees 28 minutes and the shape is tetrahedral. You can actually see the shape looking like tetrahedral itself. You must understand. Right? So it is tetrahedral. And now I write the ground state configuration of sulfur where I am sleeping. I have no intent of participating in bonding at all. So I write the ground state configuration of sulfur and I write it the outermost ground state configuration, right? So I write it the outer GSC of sulfur, that is outer ground state configuration, which is 3s2, 3px2, 3py1, 3pz1, and the entire D is vacant. D having compartments, that is D0. This is the outer configuration of sulfur in the ground state. Well, I am not showing any intent to participate in bonding. I have no intent to participate in bonding. I am just, sitting in the ground state. Now what happened? 4 oxygens called me. Because sulfate ion will be having 4 oxygens. All these 4 oxygens called me and they expressed the intent of participating in bonding with me. That is sulfur. So what they are doing? They are approaching sulfur. When they approach sulfur, they will be vomiting energy, right? But here you need to distinguish. Out of the 4 oxygens which wanted to approach sulfur, there are 2 full oxygens. Watch. There are 2 full oxygens. The other 2 are having minus charge. That means each oxygen will be having 2 unpaired electrons. So these 2 come with full 2 unpaired electrons, whereas this will come with only 1 unpaired electron because you already gained 1 electron. You must understand. So if I can write the O- configurations to you, they look like this. The oxygen configurations look like this. I write the full oxygen configuration. It is 1s2, 2s2. Look into this. This is 8. So it is 1s2, 2s2, 2px2, 2py1 and 2pz1. So you have 2 unpaired here for oxygens. You have 2 unpaired electrons for oxygens. Right? Such oxygens are number 2. 2 oxygens are approaching me that way. So the 2 oxygens are carrying in a total of 4 unpaired electrons. Total 4. Right? And what about O-? O- configuration looks like. O- will be now 9 because you gained 1 electron. O- will be 9 because you gained 1 electron. Now if you write the configuration, it looks like this. 1s2, 2s2, 2px2, 2py2 and 2pz1. And you have only 1 electron here. Only 1 electron at the 2pz. Only 1 electron in the 2pz. So understand, well, I am sleeping in the ground state with how many unpaired electrons? 2 unpaired electrons. Right? Now 4 oxygens wanted to approach me. 2 oxygens called me and say, we are coming with full unpaired electrons, that is each will be carrying 2 unpaired. So 2 oxygens will carry 4 unpaired. So I require what? 4 unpaired for 2 full oxygens. And the other O- is coming and telling me that I have 1 unpaired electron, such O- are 2. So if each O- is getting 1 unpaired, then 2 O- we require 2 unpaired. It is coming with 2 unpaired. So these 2 are coming with 2 unpaired. And the remaining 2 oxygens are coming with 4 unpaired. So 4 plus 2, I require 6 unpaired electrons in sulfur. Because this each fellow will get 1. So you have 2 such fellows, that is 2. And then each fellow will come with 2. You have 2 such fellows to be 2. So to 4. 4 plus 2, 6. And they called me in advance. They called me in advance to sulfur, who is sleeping in the ground state, and telling people that we are coming with 6 unpaired electrons. You get ready. You must be getting ready. You get ready. We are coming with what? 6 unpaired electrons. But in the ground state of sulfur, you are having only what? 2 unpaired. You are having only 2 unpaired. So you need to get into an excited state and see that the excited state stops till you get what? 6 unpaired electrons. And I told you that excited state, where you need to go into an excited state slowly. You can't jump into a straight into a the excited state what you wanted, right? So let us go slowly and get excited till we get 6 unpaired electrons. Till we get what? 6 unpaired electrons. So shall we do that? Yes, I write the first excited state for you. The first excited state configuration. Slowly we need to get excited. To which excited state you need to go, you need to check out how many oxygens are bringing it to you. 2 full oxygens will give you 4, 2 O minus will give you 2, so total 6. In ground state I have only 2, I need to get 6 and then call the partner for bonding, telling them that I am ready. That is how it works out. You must understand. So getting into an excited state should not go straight away, so slowly we will go to the excited state. So the first excited state configuration, if you see, one of the p electrons are kicked to d. So let us kick it. So it is 3s2, 3px1, 3py1, 3pz1, and in the D, now it is kicked 1, 2, 3, 4, 5, and 1 electron is kicked from P to D. Now check out how many unpaired you have. 4 unpaired you have in the first excited state. 1, 2, 3, 4. But is that enough? No, absolutely not. Oxygens have told me that they are coming 2 full and 2 O minus. 2 full is 4, 2 O minus is 2. So it is total 6 they wanted. So I must be prepared with 6 unpaired electrons, because it is only unpaired versus unpaired, they get paired, and that is how bonding is defined. So I need 6 electrons. We can't stop here. We need to get into the second excited state, and I am getting into the second excited state. Watch. The second excited state configuration of sulfur. Now here the s electron is also kicked to d. So if I can write it, it is 3s1, 3px1, 3py1, 3pz1, and in the d you have 2 unpaired electrons now. Remember, you have 2 unpaired electrons now. So you have total 1, 2, 3, 4, 5, 6. So you have 6 unpaired electrons as demanded by the oxygens before bonding. They called sulfur, see, be prepared. Be prepared. We wanted 6 unpaired from you. We will come 2 full, 2 O minus, and we will pair up with you. So the ground state sulfur is getting into an excited state and ensures that it has 6 unpaired electrons. And now I am ready. So you will get the 6 unpaired electrons only in the second excited state. Now I am ready with 6 unpaired, but still I am not in a hurry, because I need to sit in a position. I need to fix the bond angles. I need to fix the structures, sit in a position, then call the partner. Don't be in a hurry. So the next step after getting excitation is basically go for hybridization. Sit in an angle, then call the oxygens one by one, right? That is the idea. So let's go for hybridization now. Look into this. Then I go for hybridization. Then I go for hybridization of which hybridization? Which hybridization? We can calculate using the formula H is equal to half into V plus M minus E plus A, which I have already done in the beginning. And it is coming to sp3. That's where we started off the draft. Undergoes sp3, you can see here. In sulfate ion, central atom undergoes sp3, which you can find it out through the formula H is equal to half into V plus M minus E plus A. So it's basically what? sp3 hybridization. So why delay? Let us put the lock. Hybridization of 1s and 3p's, because that is how sp3 will look like. 1s and 3p's, and it is giving you sp3, 4 sp3 hybrid orbitals, bond angle 109 degrees 28 minutes, and shape is tetrahedral. Everything is fixed. Everything is fixed before bonding. So after getting 6 electrons in excited state, in the second excited state, I'm still not calling my partner. I wanted to sit in a proper position, then call the partner. So here is a hybridization. 1s and 3p's giving you 4 sp3 hybrid orbitals. So what we will do, we'll put the lock now. 1s, this is the s. When I say 1s, it is 1 3s. That's what it, don't get confused. 1s is not 1. It is not 1. It is ONE1, meaning 1s orbital. That is 1 3s. You might be checking where is that 1s, 1s, 1s. I didn't write 1s. It is written ONE1s. It is ONE1s. Mind you, it is ONE1s. That means that 1 s orbital. Now, where is the s orbital in the sulfur? This is the s orbital in the sulfur. So, it is 1s and 3p's. So, 1s and 3p's. 1s and 3p's. So, I want to lock it. This is the hybrid lock. This is the hybrid lock. 1 3s and 3 3p's will undergo hybridization, giving you 4 sp3s. So, if I can write the hybrid lock, I have 4 sp3s. 1, 2, 3 and 4. Now, what are these? These are sp3s. These are sp3s. How many sp3s? 4 sp3s, because it is 1s and 3p's. Right? So, I have 4 sp3s. And in the hybrid lock, how many electrons are participating? Let's count it. So, in this lock of hybridization, if you count the number of electrons, it is 1, 2, 3 and 4. Let us distribute it. We have to use Hund's rule. You can't put 1, 2, 3, 4 here, 2 here, 2 here, 3 here, 1 here. No, you can't do that. First go singly. 1, 2, 3 and 4. So, these 4 electrons are there in the hybrid orbitals. sp3, 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 that is 4 sp3. Must understand that. Now, don't forget to take pure p's. There are no pure p's now. The entire p is locked in hybridization. So, pure p's are 0. So, from here itself, the student must understand that pi p's are 0. Because everything has been now in hybrid lock itself. You can see here, no pure p orbitals outside. These are d. These are d. So, let us put it down. Let's put it down. These are pure d's. Now, what do you mean by pure d? Pure d is that d which have not participated in what? Hybridization. Anything which is out of the lock of hybridization is said to be pure. Pure means it is having a dumbbell shape. That's all. Right? And in the pure d's, you have 2 electrons. Let us bring it down. Now I am ready. I am totally ready. Now I am totally ready. I have done hybridization, sitting in proper position. I have 6 unpaired electrons. Now ask each oxygen to come down. Now ask each oxygen to come down. First, let us ask the full oxygen to come. The full oxygen, that means this. Let us ask it to come. And when it's coming, it is bringing 2 unpaired electrons. When it brings 2 unpaired electrons, here is the one, 2 unpaired electrons. This is oxygen in full. 1 it pairs here, which results in what? A sigma bond. And this is what it is. This is the sigma bond what I am speaking of. 1 oxygen in full came, had overlapping with the sp3 and it formed a sigma bond. Right? But it came in full, so you have the other unpaired electron. So what it will do, the other unpaired electron, this is what it is, right? This is pi dp, because the p is of this oxygen and the d is pure. So this is what is a pi bond, and which is the result of d and p. P of oxygen, d of what? Sulfur, both are pure. So one oxygen came with full, formed one sigma and one pi, formed one sigma and one pi. So similarly, get one more oxygen. Please get one more oxygen. It comes in full. When it comes in full, then here is one more sigma and here is one more pi. This is also pi dp. So the other full oxygen came, one sigma, one pi. You can see here, this is the sigma, right? And this is again one more pi d. The P of oxygen and the D of sulfur, both are pure. So two full oxygens are finished. Now we have to call the O minus, and the O minuses are 2. And what is the configuration of O minus? You can see here they have only one unpaired. They just come with one unpaired. So what they do, they come here. You have two sp3s here. This is O minus. Pair it off and you have a sigma bond. You can see here, this O minus, this is a sigma bond. That is a sigma bond because it is pairing up with a hybrid orbital of sulfur. That is nothing but what? That is nothing but what? sp3. You must understand. So one O minus is finished. The other O minus now comes with one unpaired electron, right? And then it pairs up like this. This is another O minus. This is another O minus. You can see here, this is sigma bond. That is how we construct it, right? Now what is the question? Calculating number of pi pp and pi dp bonds in this. Well, you can count it. Well, you can count this. You can count very much. You can count very much here. In this, you have total sigma bonds. Total sigma, if you count 1, 2, 3 and 4. Pi pp bonds, there are absolutely no pi pp bonds at all. Zero. It is zero. It is basically zero. You don't have pi pp bonds at all. You can see here there are only purities. So now if you see pi dp bonds, these are 2. And these are the questions in exam he will ask you. Those are the questions which he will be asking in the exam, you must understand. Well, similarly, he will ask you the pi dp bonds in sulfite ion, which we need to know. Similarly, he will ask you in SO2, SO3, SO4 minus 2, right? ClO3 minus, ClO4 minus, and all these species he will be asking to calculate number of pi pp and pi dp bonds, and this procedure must be applied.